Hey Ramblers! Tonight's video covers chapter 10.2 in our textbook and deals with congruent chords. What effect do congruent chords have on their distance from the center? Well, that's the question we want to answer. So there's a couple of theorems that are going to come up, and then we'll look at a couple of problems in the tutorials. Take good notes, pause the video often, and I hope this helps. Thanks for watching. Chapter 10.2 deals with congruent chords in a circle, and it introduces us to two theorems. The first tells us that if two chords are equidistant from the center of a circle, then the chords are congruent. Well, let's take a look at that proof. Here we know that since the two chords are equidistant from the center, xp must be congruent to py. Of course, we're given circle P, and we know that the segments that measure the distance from the center must meet the chords at right angles. So let's mark that in. Okay, we're going to draw PB and PC because you'll find with circles that it's always a good idea to put the radii in, because you'll recall that all radii of a circle are congruent. Oops. There we go. So we know that PB must be congruent to PC. And since these angles at x and y are right angles, I know that triangle PXB is congruent to PYC by HL, which makes BX, this half of the chord, equal to this half of the chord, which requires that AB be congruent to CD, because since each one of these is a half of the full chord, the chords must be congruent. Okay, so it's pretty clear that Theorem 77 is true. Now, let's take a look at Theorem 78. Theorem 78 is the converse of Theorem 77. And here we're told that if the two chords of a circle are congruent, then they are equidistant from the center of the circle. Let's quickly look at 77 again, and you'll notice that, yeah, it is definitely the converse. Because the given in 78 deals with two congruent chords, and that's the conclusion of Theorem 77. Whereas the conclusion of 78 talks about the chords being equidistant from the center, and that's the given of Theorem 77. So Theorem 77 is definitely the converse of 78. So let's take a look at the proof. Okay, we're given circle P, and we know that the chords AB are congruent to CD. Of course, PB and PC are congruent because they're radii of the circle. Now, since this is the segment measuring the distance from the chord to the center of the circle, by definition, those have to be perpendicular. The chord and the line from the center have to be perpendicular, so those are right angles. So it's pretty clear to see that since these chords are congruent, half the chords will be congruent by like divisions, and so the triangle XBP will be congruent to triangle YCP by HL. Therefore, by CPCTC, PX is going to be congruent to PY. And that's what we had to prove. So QED. Alright, so let's make sure you have those two theorems down. That if the chords are congruent, they're equidistant from the center, and conversely, if they're equidistant from the center, then the chords are congruent. Let's take a look at a couple of examples in the tutorials, and we'll conclude the video. Thanks for watching. Number 2 on page 447 tells us that PQ is congruent to PR, and that they tell us AB, this entire segment or a chord, is 6x plus 14, and CD, the other chord, is 4 minus 4x. Well, what conclusion can we draw from the fact that QP is congruent to PR? Hopefully you recognize that that means the two chords are congruent. So I can set 6x plus 14 equal to 4 minus 4x and solve for x. That gives me that x equals -1. And in order to solve for AB, I plug -1 back into the expression for AB, which is 6 times x plus 14, which equals 8. So AB equals 8. Okay, number 15 on page 449 is really challenging. It tells us that AF is 6 and that ED is 1. Since we know that it is circle E, then an EF is perpendicular to AC. AC must be bisected. So FC is also 6. They want us to find the radius, and I'm going to label AE as my radius. And take a look at what we have. Triangle ADC is similar to triangle AFE. In drawing the triangles, I can set up the proportion that AD over AF equals AC over AE. When I plug in my values, I see that R plus 1 over 6 equals 12 over R. If I cross multiply this proportion, I get R squared plus R equals 72. Solving for R, this quadratic becomes R squared plus R minus 72 equals 0. So that must be R plus 9 times R minus 8, so R equals 8. Okay, when they ask us to find the perimeter of triangle ABC, we know that the two legs are 12 and 12, so that gives us 24. But in order to find BC, we recognize that this is an isosceles triangle with an altitude drawn to the base of that isosceles triangle, therefore bisects it. So I'm going to solve for the right triangle ADC and solve for the leg DC. Solving, I find that DC equals 3 root 7. So therefore BC must equal 2 times that, or 6 root 7. Bringing that number up to my to 24, I can see that the perimeter equals 24 plus 6 root 7. Thanks for watching.